The first proof of life beyond Earth may be locked inside a rock no bigger than your hand. Not in a ruined city. Not in a fossilized bone. Not in a strange skeleton half buried beneath red dust. Not in a footprint. Not in a shell. Not in a shape so familiar that the human mind can immediately call it alive. If Mars ever gives us the evidence people have been waiting for, it may come through something far colder, smaller, and harder to read. A thin cylinder of stone, drilled from an ancient outcrop, sealed in a metal tube, and left waiting on a planet that no longer tells its story out loud. That is what makes this search so tense. The evidence, if it exists, may not look like evidence. It may not announce itself. It may not survive as a body, a cell, or even a clean chemical message. It may be a pattern in minerals, a stain around a grain, a cluster of organic molecules in the right place, or the wrong place, a texture that makes sense only when the rock, the water, the sediment, the chemistry, and the age of the landscape are all brought into the same room and forced to answer the same question. Could life have done this? Mars does not make that question easy. From the surface, the planet looks emptied out. The sky is thin, the cold is severe, and the ground has the color of iron left too long in the weather. Dust covers everything. It lies in the shallow dips between stones, gathers against rover wheels, drifts across old tracks, and softens the edges of a landscape that has had billions of years to become still. Nothing moves there with hunger, nothing grows there into the light, no animal crosses the frame, no water breaks against a shore. The entire world seems to have been reduced to rock, wind, and memory. Yet the memory is the problem. Mars is not a simple desert, it is a desert with river valleys. It is a dry planet with lake beds. It is a dead surface marked by the architecture of ancient water. From orbit, the shapes are impossible to ignore. Channels cut through terrain, sediment fans spread into basins, layered deposits exposed by erosion, minerals that formed in the presence of water. These are not fantasies drawn through bad telescopes. They are geological structures, measured and mapped by spacecraft, photographed by rovers, studied for decades by people who know that water alone is not life, but also know that life, as we understand it, cannot be discussed honestly without water. That is why Jezero Crater matters. Long before a machine from Earth landed there, Jezero was an impact wound. A crater blasted into the Martian crust by violence. Later, water entered that wound, river channels spilled into it. A lake formed, sediment was carried in, dropped, layered and buried. A delta grew where moving water slowed and lost its load. On Earth, a delta is not just a shape, it is a recorder. It collects mud, sand, clay, organic material, minerals, and chemical signals from a larger landscape. It can bury fragile evidence quickly enough to protect it. It can turn a living environment into a geological archive. On Mars, that archive froze into stone. Perseverance was sent there because the crater gives science a real target. Not a vague hope. Not a red planet myth. A specific ancient environment, where water once stood, where fine sediment once settled, where rocks may have formed in conditions that could preserve signs of past microbial life, if such life existed. The rover is not wandering randomly across Mars, hoping to stumble into a miracle. It is moving through a carefully chosen crime scene, where the victim may be a vanished habitable world, and the evidence may be locked inside rocks that look ordinary until they are read at the smallest scale. That reading is brutally difficult. A rock can say water was there without saying life was there. It can contain organic molecules without proving biology. It can show minerals produced by chemical reactions that microbes use on Earth, while still being entirely non-biological. It can form spots, veins, halos, and textures that look suggestive, then turn out to be the work of fluids, heat, acidity, radiation, or mineral growth. Mars is allowed to be chemically interesting without being alive. That one sentence has to stand guard over the entire investigation. There is no honor of this story where Mars life is already confirmed. There is also no honest version where the rocks do not matter. Perseverance works in that narrow space between hype and dismissal. It studies the ground with cameras and instruments. It selects targets, abrades weathered surfaces, exposes fresh material, maps chemistry, and drills cores from rocks that may preserve ancient environments. The drill does not cut a dramatic object. It removes a cylinder of stone, narrow and pale against the red dust, something that could be mistaken for a dull sample from a construction site if you did not know where it came from. Then, the rover seals it inside a pristine tube, turning a piece of Mars into evidence for a future laboratory. That tube is a promise with no guaranteed ending, it says. This rock is worth asking again. This rock should not be judged only by the tools that can fit inside a rover. This rock may need Earth's laboratories, Earth's microscopes, Earth's mass spectrometers, Earth's clean rooms, Earth's arguments, Earth's patience. A rover can identify a suspect. It cannot conduct every interrogation. A sample return mission, if it can be done, would bring the suspect home. Until then, the answer remains on Mars. This is the strange cruelty of the mission. The most important evidence may already have been collected, but not yet understood. It may be sitting inside a tube, sealed against contamination, waiting for a retrieval architecture that has become one of the hardest and most debated problems in planetary science. The rock may hold only geology. It may hold a false alarm that teaches scientists how Mars can imitate biology. It may hold a signal too damaged to settle. Or it may hold a pattern that, once tested in Earth laboratories, becomes hard to explain without ancient microbial life. The entire story is built on that uncertainty. Human beings are bad at uncertainty. We want the rock to be proof or nothing. We want the announcement, the headline, the clean sentence. Life found, life not found. But Mars does not owe us that kind of sentence. Ancient rocks rarely speak in clear language, even on Earth. The older the possible evidence, the more it has been altered, buried, heated, fractured, weathered, or chemically rewritten. The study of ancient life is often not the study of bodies. It is the study of traces that may have survived after the bodies disappeared. On Earth, the oldest life evidence can be disputed for exactly that reason. Minerals can mimic biology. Biology can alter minerals. Carbon can move, textures can deceive. Time can erase the difference between a living process and a non-living one, until only a cautious interpretation remains. And Earth is the easy case. Earth has oceans, active biology, field sites, laboratories, and direct access. Mars gives us images, data, and a few carefully chosen samples still sitting millions of kilometers away. That distance turns every clue into a pressure chamber. Consider what Perseverance is actually doing when it drills. It is not simply collecting rocks. It is trying to reach below the damaged skin of Mars. The surface is exposed to radiation and oxidants. Molecules near the surface can be broken apart. Textures can be altered. Dust can hide details. A fresh core taken from inside an outcrop has a better chance of preserving the ancient environment than the exposed surface does. The drill, in that sense, is a time machine with a narrow mouth. It bites into a dead landscape because the inside of the rock may remember what the outside has lost. The rover's movements have a heavy patience to them. It does not race across Jezero. It cannot. It drives in measured segments, stops, looks, waits for instructions, studies hazards, and returns data to Earth. People examine the terrain from millions of kilometers away and decide where the next question should be asked. A patch of layered stone becomes a target. A vein becomes interesting. A color difference matters. A texture is scrutinized. The scale of the question is cosmic, but the work itself is exacting, local, almost intimate. A wheel track in dust, a camera pointed at rock, a drill mark under a thin sky. That is what the search for life looks like when the romance is stripped away. It looks like geology, and that is why it might work. The old dream of Mars was too loud. It imagined canals, civilizations, invaders, ruined cities, dying intelligence. It turned the planet into a mirror for human fear and hope. Modern Mars is quieter and more unsettling. It asks whether life can be so small and fragile that an entire world can lose it without leaving anything obvious behind. It asks whether biology can flicker in mud, alter chemistry, disappear, and leave only a mineral whisper that future instruments struggle to hear. It asks whether a living planet can become a dead archive. That is more haunting than monsters. A monster can be photographed. A vanished microbial world has to be reconstructed from stone. The reconstruction begins with water, but it cannot end there. Ancient Mars had water in places. Jezero held a lake. A river built a delta. Those are powerful facts. They are not enough. Water is a condition, not a conclusion. On Earth, water-rich environments can teem with life, but water can also flow through places that remain sterile. A lake can be habitable and uninhabited. A sediment can be well preserved and biologically empty. A planet can come close to life and never cross the threshold. That possibility is just as important as the other one. If Mars had habitable environments and no life, Earth becomes stranger. The existence of water, organic chemistry, minerals and energy would not be enough. Something else would have been required. The origin of life would look less like an automatic planetary process, and more like a difficult event, dependent on conditions we still do not fully understand. A sterile Jezero would not be a failure. It would be a severe answer. But if Mars did have life, even microbial life, the meaning is almost impossible to contain. It would not mean Mars once had forests or animals. It would not mean the old fantasies were right. It would not mean cities under sand, or faces carved by intelligence, or messages hidden in rocks. It would mean something smaller and more profound, that biology appeared or survived beyond Earth, in our own solar system, on a world close enough for machines to touch. The universe would not become crowded overnight. But Earth would no longer stand alone in the only way that has ever mattered. One additional example changes the silence. That is why a rock core can carry so much emotional weight. It is not impressive in size. It does not look like a revelation. Yet, if it preserves the right pattern, in the right context, with the right chemistry, and if every non-biological explanation weakens under scrutiny, that rock could become one of the most important objects ever handled by human beings. The evidence would need to be mercilessly tested. A serious claim of ancient Martian life would not rest on one image or one instrument reading. It would need convergence. The minerals would have to make sense. The organic chemistry would have to make sense. The textures would have to make sense. The sedimentary environment would have to make sense. The age and alteration history would have to make sense. Contamination would have to be ruled out. Abiotic processes would have to be modeled, tested, and pushed hard. Independent labor would have to repeat and challenge the work. Only then could the word life move closer. This is why the phrase potential biosignature matters so much. It is not a trick. It is not a weak version of proof. It is a technical warning label attached to evidence that may have a biological origin but does not yet allow a conclusion about life. The phrase holds the door open without pretending to know what is behind it. It is the correct language for a rock that deserves attention, but not belief. Chiava Falls, and the Sapphire Canyon sample taken from it, belongs to that uncomfortable category. The rock drew attention because it came from a setting tied to ancient water. It contained features that made scientists ask whether microbial processes might be part of the story. But the careful boundary remains. The evidence does not confirm life. It does not show a fossil. It does not remove non-biological explanations. It is intriguing enough to matter, not decisive enough to settle the case. That is the kind of object that makes planetary science tense. Not because it gives an answer, because it refuses to be ignored. A lesser story would turn Chiava Falls into a miracle. A cynical story would throw it away because it is not proof. The serious story holds it in place and says, this is why samples matter. This is why context matters. This is why rover data are powerful but limited. This is why Mars rocks need Earth laboratories. This is why a future return mission is not just another engineering dream, but the next stage of the evidence chain. A sample tube is part of that chain. The chain begins with ancient water moving through rock and sediment. It continues with deposition, burial, alteration, exposure, rover selection, drilling, sealing, caching, retrieval, return, curation, laboratory analysis, peer review, disagreement, and maybe, only maybe, consensus. Discovery does not happen at the drill. It begins there. That beginning is quiet enough to miss. A rover arm lowers, dust shifts, a bit presses into stone. The drill turns, powder gathers around the hole, a core is captured. The surface of Mars has been touched, not by a hand but by a machine carrying human curiosity in metal form. There is no dramatic music on Mars. There is only the thin atmosphere, the cold light, and the silence of a landscape that has waited billions of years to be questioned. Inside the core, the past is compressed. Sedimentary rock is time made physical. Grain by grain, layer by layer, it records movement and stillness. A river carries material. A lake receives it. Fine particles settle through water. Minerals form as chemistry changes. Fluids pass through pores. Later, burial turns sediment into rock. Later still, erosion exposes the rock again. By the time a rover reaches it, the original environment is gone, but not entirely lost. Its remains are arranged in grains, minerals, fractures, veins, and textures. A living environment, if it existed, would have been part of that arrangement. Microbes do not need to become fossils in the obvious sense to leave traces. On Earth, microbial life can alter chemical gradients. It can influence mineral precipitation. It can produce organic compounds. It can form biofilms that trap and bind sediment. It can change redox conditions around iron, sulfur, carbon, and other elements. But the trap is that non-living processes can also alter minerals, move carbon, form spots, create veins, and generate complexity. The same categories that make biosignatures possible also make false positives possible. This is why Mars life detection is not a yes or no checklist. It is a battle over explanation. A rock may contain carbon. Where is it? What form is it in? Is it associated with minerals that suggest a habitable environment? Could it have arrived from outside Mars? Could it have formed through abiotic chemistry? Has radiation changed it? Is it concentrated in textures that matter, or spread without biological pattern? A rock may contain iron minerals. Which ones? How did they form? What temperature? What fluid chemistry? Were organics involved? Did the reaction happen during deposition, or much later? Could water-rock reactions produce the same result without life? A rock may contain spots or halos. Are they growth textures, alteration features, reduction spots, oxidation patterns, or something else? Are they tied to cracks, to veins, to organic material, to specific layers? Do they repeat in ways that point to a process, or do they appear randomly? The evidence lives in relationships. A single signal is weak. A signal connected to the right environment grows stronger. A chemical pattern embedded in sedimentary context grows stronger still. A texture that fits the chemistry in a rock formed under conditions compatible with life, with abiotic explanations increasingly strained, becomes harder to dismiss. The goal is not to find something that looks biological at a glance. The goal is to find a web of evidence that remains coherent when every non-biological pathway is given a fair chance. That is a high standard. It has to be. The claim would be too large for anything less. The history of Mars exploration is full of lessons about caution. The planet has repeatedly offered suggestive evidence without delivering final proof. Images raised hopes. Chemistry raised questions. Meteorites from Mars provoked arguments. Methane reports stirred debate. Organic molecules were detected in some settings, but organics are not organisms. Habitable environments were found, but habitability is not habitation. Each step mattered. None ended the search. Perseverance is different because it was sent not only to study Mars, but to prepare evidence for Earth. That changes the nature of the mission. The rover is both explorer and collector. It is selecting a library of Martian rocks that future scientists may study for decades. The samples are not random. They come from documented locations, tied to geological context, chosen to represent important environments in Jezero's history. Some may be volcanic, some sedimentary, some altered by water, some may help date events, some may test habitability, some may become central to the search for ancient life. A library can contain an answer no single page reveals by itself. If the samples return, scientists will compare them. They will not study Sapphire Canyon in isolation. They will ask how its chemistry relates to other rocks from the crater. They will ask whether similar features appear elsewhere. They will reconstruct environmental change across Jezero. They will test whether the potentially suggestive patterns belong to a local process, a regional process, or something more significant. The strength of the argument may come not from one sample, but from the pattern across many. Mars, however, has not yet given those samples back. That is where the sample return question becomes the central tension. Collecting the rocks was already hard. Bringing them to Earth is harder. A future system would need to retrieve sealed tubes, load them into a vehicle, launch them from the Martian surface, move them through orbital transfer, bring them across interplanetary space, and deliver them safely to Earth under strict contamination controls. Each step has engineering risk. Each step costs money. Each step must be justified against other missions, other priorities, other scientific dreams. The rock is small. The mission around it is enormous. That contrast is almost absurd. A hand-sized core can demand rockets, orbiters, clean rooms, international planning, budget battles, and years of work because the question inside it is that large. It is not just a rock, it is a possible answer to whether life ever began beyond Earth. The answer may still be no. That must remain present. A sober story has to allow disappointment. It has to allow that the returned samples may show ancient water, complex chemistry, and no sign of biology. It has to allow that Shiava Falls may become an important example of abiotic processes on Mars. It has to allow that potential biosignatures may remain potential forever. It has to allow that nature may imitate life more convincingly than we expect. But disappointment in this context would not be empty. A false biosignature teaches scientists what to avoid. A sterile lakebed teaches scientists about the boundary between habitability and life. An ambiguous sample teaches scientists what instruments and targets future missions need. Mars can still transform science, even if it never gives us biology. This is not a story where only confirmation matters. It is a story where evidence matters. The rover's tracks in Jezero are therefore not just tracks across terrain. They are tracks across a question that has been shrinking and sharpening for generations. Once, people asked whether Mars had civilizations, later, whether it had canals, then whether it had water, then whether it had habitable environments. Now the question has narrowed to specific rocks, specific samples, specific mineral patterns, specific cores that may someday be opened under laboratory lights. This narrowing is not a loss of wonder, it is wonder becoming disciplined. The closer science gets to a real answer, the less it resembles fantasy. The images become less theatrical. The language becomes more careful, the evidence becomes smaller, the claims become harder, the public spectacle fades, and the work becomes more intense. That is the paradox of astrobiology. The most revolutionary discovery may arrive through the least spectacular object, a small rock, a sealed tube, a laboratory result that takes years to trust. The world may change quietly. Picture Jezero when it held water, not as a paradise because that would be too easy, not as a blue earth under a red sky. More likely it was harsh even then. Cold at times, unstable, exposed to impacts and volcanic influence, governed by a climate still debated. The lake may have changed depth, water may have come and gone, sediment may have arrived in pulses. The delta may have advanced during wetter intervals and dried during harsher ones. Ancient Mars does not need to have been gentle to have been habitable. Life on Earth often survives in places humans would call hostile. The real question is whether Jezero offered a foothold. A foothold can be small: a wet sediment layer, a protected pore space, a chemical gradient where energy can be harvested, a mineral surface where organic molecules concentrate, a zone where water persists long enough for chemistry to become biology, or for biology to leave a trace. Life does not begin with grandeur. It begins with mechanisms. That is why microbes matter. They are not disappointing substitutes for aliens. They are the form life takes when the question is most fundamental. A microbe can alter a planet. A microbial biosphere transformed Earth long before animals existed. It oxygenated the atmosphere over deep time, shaped sediments, changed chemistry, and prepared the world for everything that came later. If Mars ever had microbes, even briefly, that would be enough. The universe does not need Martian animals to become biologically interesting. One cell would be a revolution. One convincing trace of ancient cells would be a revolution. But the trace has to be real. There is a difference between wanting Mars to have lived and proving that it did. The desire is understandable. A living Mars would make the universe feel less lonely. It would give human beings another origin story to compare with our own. It would make every icy moon and distant planet feel more promising. But desire can contaminate interpretation as surely as dust can contaminate a sample. A serious investigation has to control for hope. That control appears in the language scientists use: potential, candidate, consistent with, could have. Requires further study. Alternative explanations remain. These phrases can sound disappointing to people trained by headlines, but they are the vocabulary of intellectual honesty. They do not weaken the story. They make the story trustworthy. A possible biosignature that survives careful language is more interesting than a false claim dressed up as certainty. Mars has been overclaimed too many times. The rocks deserve better. A rock like Shayava Falls is powerful because it forces attention onto the evidence itself. It does not let us escape into fantasy. It asks what minerals are present, how they formed, what organic signals mean, why the texture appears where it does, what ancient water did to the rock, and whether known abiotic processes can explain it. It asks for patience. It asks for Earth. That last demand is the most frustrating. The rover is there, the sample is there, the data are there, yet the final tools are here. Humans have sent a geologist to Mars in robotic form. But the deepest reading of the evidence may require bringing Mars back to the geologists. This is why the sample tubes feel almost unbearable. They are small containers of deferred knowledge. Each one is a piece of another planet placed under seal. Not because its meaning is known, but because its meaning might become knowable later. In a culture addicted to immediate answers, a sample tube is an act of scientific patience. It accepts that the most important result may belong to the future. The future, however, is not guaranteed. Missions can change. Budgets can tighten. Architectures can be redesigned. Priorities can shift. Mars sample return has been treated as one of planetary science's most important goals. But its path has been difficult. The challenge is not just technical. It is institutional, financial, and political. That gives the rock a new kind of vulnerability. A sample can survive billions of years on Mars, and still depend on human decision-making to complete its journey. The universe can preserve the evidence. Humanity can still fail to retrieve it. That tension should not be hidden. It is part of the drama. The search for ancient life is not only a scientific investigation. It is a test of whether we can sustain a long chain of curiosity across decades. It requires one mission to collect, another to retrieve, another to return, and many more years to analyze. It requires people who may never see the final result to build the steps that make the result possible. A civilization that wants quick answers may struggle with a question this slow. Mars has no obligation to speed up. The planet has already waited billions of years. The rover moves through what remains. Its cameras see cliffs, rocks, dust, and layers. The images come back to Earth, where they are stretched across screens and studied by eyes trained to notice slight changes in color, grain size, bedding, fractures, and texture. To most viewers, the images can look repetitive, rock after rock, red ground after red ground, but a planetary geologist sees time, a sedimentologist sees transport and deposition, an astrobiologist sees preservation potential, energy gradients, and places where chemistry may have crossed into biology or come close enough to imitate it. The same image can be dull or electric, depending on what question you bring to it. A small outcrop can be a wall of ancient evidence, a vein can be a record of fluid movement, a spot can be a chemical event. A layer can be a lake breathing in sediment and going still. The audience has to be brought into that way of seeing. The rock becomes suspenseful when it stops being background and becomes testimony. It becomes central when every mineral is a possible witness and every alternative explanation is a suspect. This is why a detective tone fits Mars better than a triumphal one. The planet is not presenting a trophy. It is presenting a case file with missing pages. A detective does not decide the answer because one clue looks dramatic. A detective asks what the clue means, where it came from, whether it fits the timeline, whether it could be planted, whether it connects to other evidence, whether another explanation is cleaner. In the search for ancient life, geology is the crime scene and chemistry is the witness statement. The suspect is biology, but biology is not convicted by suspicion. Every non-living process must be allowed to defend itself. Water-rock reactions can produce unexpected mineral patterns. Organic molecules can be delivered from space. Iron and sulfur chemistry can proceed without cells. Phosphorus can be present because rocks contain it, not because life used it. Veins can form when fluids move through fractures. Spots can form when chemical fronts alter minerals. Sedimentary layers can preserve habitable environments without preserving organisms. The non-biological universe is not simple. It can be inventive, and it has had billions of years to work. That is why the evidence must be cumulative. If a returned Martian sample ever convinces the scientific community, it will likely do so by making the non-living explanations increasingly awkward. Not impossible in a philosophical sense, but strange. Biology would have to explain the pattern better. The rock's environment would need to support the interpretation. Multiple measurements would need to converge. The signal would need to be located in context, not floating alone. The goal is not absolute certainty beyond imagination, it is a level of evidence strong enough that life becomes the best explanation. That standard has history behind it. On Earth, ancient biosignatures are evaluated through multiple lines of evidence, because no single feature is safe. Morphology alone can mislead, chemistry alone can mislead, isotopes alone can mislead, context alone can mislead. Together, they become stronger. The same logic must apply on Mars, with even more caution, because Mars is unfamiliar and inaccessible. The danger is not only false positives, there are false negatives, too. A real biosignature may be missed because it is too degraded, too subtle, or too unlike what Earth has trained us to recognize. Search is biased by the only biology we know. Instruments are designed around known life's chemistry. Interpretation is guided by Earth analogs. That is necessary, but limiting. Mars may have hosted life that used familiar chemistry, or it may have produced signals that sit at the edge of our recognition. Ancient microbial life may leave evidence that we overlook, because it does not match our expectations cleanly. So the investigation has to be both skeptical and imaginative. Too much imagination, and every rock becomes alive. Too much skepticism, and a faint real signal is crushed before it is understood. The right posture is tense, disciplined attention. That tension defines perseverance's work. The rover is not proving life day by day, it is building the conditions under which proof, or strong disproof, may someday be possible. Every sample is chosen because it contributes to a larger story. Every context image matters. Every instrument reading matters. Every sealed tube preserves a chance to ask deeper questions later. The rock is the protagonist because it carries the conflict inside itself. It may be ordinary, it may be extraordinary, it will not tell us which until we earn the answer. Modern Mars looks like a place after the end of a story. The rivers are gone, the lake is gone, the atmosphere is thin, the surface is cold. But the rocks suggest that the story had earlier pages. Jezero's delta is one of those pages. It says that water moved through this world. It says sediment accumulated. It says conditions changed. It says the crater once belonged to a different Mars. A delta is a structure of slowing down. Water moving with energy enters a basin and loses force. Sediment falls out. Coarser grains drop sooner. Fine material travels farther and settles in quieter water. Layers form according to flow, chemistry, and time. In those fine sediments, on Earth, organic material can be protected. Microbial communities can become part of the record. Not always, not automatically, but often enough that a Martian delta becomes one of the rational places to look. That is the key word, rational. This is not belief. It is target selection. Jezero was not chosen because it looked romantic. It was chosen because its geology made sense for the question. Ancient lake, river delta, sedimentary deposits, preservation potential, access to multiple rock types. A place where the search for past habitability and possible biosignatures could be conducted with context. The mission's strength is that it treats Mars as a place with history, not as a backdrop for speculation. The weakness, if it has one, is that history has been damaged. Billions of years are not gentle. Mars has been struck by impacts, scoured by wind, altered by fluids, chilled, dried, irradiated, and exposed. Surface rocks can be modified long after they form. A biosignature from an ancient lake environment could be overprinted by later chemistry. A sample could contain multiple histories layered together. The evidence may not be a clean page. It may be a palimpsest, written over again and again. That does not make it useless, it makes interpretation hard. Hard is not hopeless. The best science often comes from damaged evidence. A crater tells impact history because it is damage. A fault tells stress because rock broke. A fossil tells life because living tissue became mineral and sediment. A sedimentary layer tells environment because particles were moved, buried, and changed. Mars rocks are difficult because they have been altered, but alteration is also information. It reveals fluids, temperatures, chemistry, exposure, and environmental change. The trick is knowing which changes happened when. If a mineral formed while the lake existed, it may tell one story. If it formed millions of years later when fluid moved through cracks, it tells another. If organic molecules were present during deposition, that matters differently than if they arrived later. If spots formed in ancient wet sediment, that is different from spots formed by later alteration. Time order becomes critical. A rock is not just material, it is sequence. Perseverance's instruments help build that sequence. But they cannot complete it. They can map elemental chemistry at small scales. They can identify minerals and organics with onboard tools. They can image textures. They can choose where to drill. But Earth laboratories can go deeper. They can study isotopic ratios with much higher precision. They can prepare ultrathin sections. They can use electron microscopy, nanoscale analysis, synchrotron techniques, and many forms of organic characterization. They can run experiments to reproduce possible abiotic pathways. They can distribute tiny portions to independent teams. A rover observes under constraint. A laboratory attacks the sample from every side. That is why bringing the rocks home is not an optional luxury. For the life question, it may be the difference between suspicion and knowledge. And yet the return is not simple. Mars has gravity. Launching from its surface requires a rocket that has never been launched from another planet. The samples must be transferred without being lost or contaminated. The return capsule must protect Earth and preserve the material. The curation facility must be prepared to handle samples that may contain sensitive chemical evidence, and however unlikely, must be treated with planetary protection seriousness. The mission is a chain where each link matters. The rock no bigger than your hand becomes the reason for an interplanetary relay. That is how science sometimes works. The smallest object can require the largest effort because its meaning is disproportionate to its size. A single returned sample can become a permanent reference for Mars. It can be studied with instruments that do not exist yet. It can be revisited when new questions emerge. It can be compared with meteorites, rover data, orbital maps, and future samples. It can sit in a collection the way lunar samples have done, still producing science long after their return. But Mars samples would carry an additional tension. They would be pieces of a world where life may once have had a chance. The chance is what keeps the story alive. Not certainty, chance, a cold, disciplined, evidence-based chance that ancient microbial life may have lived in or near environments like Jezero, and that some trace may have survived in sedimentary rock. That possibility is neither fantasy nor conclusion. It is a reason to drill. The rover's drill marks are therefore among the most serious marks humans have ever made on another planet. They are not footprints of conquest. They are questions cut into stone. If the rock comes home and shows nothing biological, the drill mark still mattered. It selected a piece of Mars that helped us understand climate, water, sedimentation, and planetary change. If the rock shows an ambiguous signal, the drill mark mattered, because it revealed the limits of our methods, and the need for better ones. If the rock shows a strong biosignature, the drill mark becomes historic. In all outcomes, the rock matters. That is why the story must stay centered on it. A Mars documentary can easily scatter into everything at once: volcanoes, dust storms, colonization, terraforming, rovers, satellite, ice, methane, human missions. Those topics are compelling, but they would dilute this investigation. The dramatic center here is not Mars as a destination. It is Mars as an archive. The question is not whether humans will walk there. The question is whether something once lived there and left a trace in stone. The rock holds the camera. The rover exists because of the rock. The ancient lake matters because it made the rock possible. The sample return debate matters because the rock has not yet been fully read. The laboratory matters because the rock may be too subtle for Mars-based instruments alone. The human expectation matters because the rock may disappoint or transform it. Everything circles back to the stone. There is a reason that feels emotionally right. Life itself, when pushed into deep time, becomes geological. The bodies vanish, the organisms vanish, the environment changes. What remains is rock. If we want to know whether life existed billions of years ago, we have to ask rocks to remember what living things could not preserve directly. On Earth, that is already difficult. On Mars, it becomes almost severe. But Mars may be better at preservation in certain ways. Its lack of plate tectonics like Earth's means some ancient terrains remain accessible. Earth constantly recycles crust through tectonics, erosion, burial, and metamorphism. Much of Earth's earliest record is gone or heavily altered. Mars, though damaged differently, preserves ancient surfaces across huge regions. A Martian rock can be unimaginably old and still reachable by a rover. A dead planet may keep old pages that Earth has torn out. That is one of the deep ironies of the search. Mars died at the surface, but death may have preserved parts of its youth. The loss of active geology on the scale Earth experiences may have left ancient records exposed. The same planet that became hostile to life may have become useful for studying whether life ever had a foothold there. The archive is harsh, but real. Jezero's archive is especially compelling because it combines ancient water with sedimentary preservation. The crater does not merely say water existed somewhere on Mars. It shows a system, inflow channels, a basin, a delta, layers. It gives scientists a way to connect rocks to processes. That connection is what turns an interesting sample into evidence with context. Context is the word that keeps returning, because without it the search falls apart. An organic molecule in isolation is a clue with no address. A mineral spot without environment is a shape with no story. A possible biosignature without stratigraphy, alteration history, and comparison becomes vulnerable to wishful thinking. But a sample embedded in a mapped sedimentary sequence can be interrogated properly. Its meaning can be constrained. Mars cannot be cross-examined directly. Its rocks can. The cross-examination is slow. It begins with what the rover can do. It continues with what Earth labs may do. It does not end with one team. A credible life claim must survive people who do not share the same excitement. It must survive skeptics, competing models, new instruments, and time. That is not a weakness. It is why science can make claims larger than any individual hope. A rushed Mars life announcement would damage the field. A careful one, if it ever comes, would change history. That future may begin with a sample that looks underwhelming. A core sample does not look like a plant's secret, it looks like a fragment. But the human eye is the wrong instrument. The important features may be microscopic, molecular, isotopic, structural. They may require mapping at scales far below the grain. They may require knowing whether carbon and minerals occur together in meaningful patterns. They may require distinguishing organic matter, formed by life, from organic matter formed without it. The eye wants a fossil. The evidence may offer a distribution. That mismatch between expectation and reality is part of the drama. People are trained by movies to expect alien life as a visible encounter. Science may deliver it as an inference from stone. No face, no movement, no signal. Just a set of measurements that, combined, become harder and harder to explain without biology. The quietness of that possible discovery does not make it smaller. It makes it more unsettling. If life can be hidden so deeply in the record that only a returned rock reveals it, then the universe may be full of worlds whose histories we cannot read from a distance. Telescopes can study atmospheres, orbiters can map surfaces, rovers can analyze targets, but life, especially ancient microbial life, may often require touch. It may require samples. It may require patience. It may not announce itself across light years. Mars is close enough for touch. That is why it matters. The search for life elsewhere often looks outward to distant exoplanets, and those worlds are important. But Mars is the world where the question can become physical. We can drill it, we can seal it, we can return it. We can place it under a microscope. The scale of the universe is vast, but the evidence may come from a single core on a neighboring planet. That contrast gives Mars its strange power. The planet is not the most Earth-like world in the present. It is not the most promising place for life today compared with some subsurface ocean worlds. But it is accessible in a way those worlds are not. Its ancient rocks are exposed. Its history overlaps with the early history of terrestrial planets. It offers a test case for whether life can emerge or leave traces in a world that once had water and then lost surface habitability. Mars is a laboratory for planetary failure, maybe also for planetary life. To read that laboratory, scientists must resist turning every discovery into destiny. Ancient lake evidence does not mean microbes. Potential biosignature does not mean confirmed biosignature. Organic carbon does not mean biology. Mineral spots do not mean fossils. Sample return does not guarantee an answer. Every phrase has a limit. The limits are not obstacles to storytelling. They are the story's moral structure. A mature, documentary voice should let the uncertainty breathe. It should show the rover alone on the surface, then cut into the rock, then pull back into ancient Mars, then move into the future laboratory, then return to the sealed tube waiting under a cold sky. The rhythm should feel like an investigation narrowing around a piece of evidence. Not loud, not triumphant, pressurized. A rock no bigger than your hand. That image is strong because it compresses the entire question. In one hand, If it ever reaches Earth, there could be a piece of a Martian delta, formed when water moved through Jezero, altered by chemistry, preserved through deep time, drilled by perseverance, sealed inside a tube, returned across space, and opened by scientists trying to decide whether life once touched it. The object is small enough to hold, the implications are too large to hold. That is the kind of scale science can create. The hand becomes planetary, the stone becomes cosmic, but the stone must remain a stone until the evidence says more. The temptation to personify it, to make it a messenger, must be controlled. It may contain no biological memory. It may contain an ambiguous one. It may contain a misleading one. The rock does not care what humans need from it. It has no duty to complete our story. That indifference is part of Mars's power. Earth is full of life answering life. Mars is not. Mars gives no comfort. It shows what a planet can become when surface habitability fails or never stabilizes. It is a reminder that worlds are fragile in ways human imagination often avoids. A planet can have water and lose it. It can have environments that might support life, and then become hostile. It can preserve the shape of a lake, without preserving the lake. It can hold the memory of rivers in a place where no river will flow again. If Mars once had life, that life lived under a future of extinction. If it did not, the ancient lake was a stage without actors. Both possibilities are haunting. The rock sits between them. This is why the search cannot be reduced to optimism. Optimism alone would make the evidence too easy. Pessimism alone would make the mission pointless. The right feeling is pressure. The knowledge that something important may be present, and the discipline not to name it too soon. That pressure is visible in every careful statement about potential biosignatures. It is visible in the effort to return samples. It is visible in the way scientists talk about Shayava Falls not as proof, but as a candidate worthy of deeper study. A candidate can change everything without yet proving anything. That is hard to explain in a headline, but it is central to real science. The sample does not have to be confirmed life, to be one of the most important rocks ever collected. It only has to be the best available test of a question humanity has carried for generations. Its value lies in the quality of the question it lets us ask. Can a rock from an ancient Martian river lake environment preserve evidence of microbial processes? That question is precise enough to attack. It is also large enough to matter. The answer may depend on the details of minerals such as iron-bearing phases, sulfur chemistry, phosphate distribution, organic carbon, and the relationships between them. It may depend on whether features formed in low-temperature water compatible with life, or through later alteration. It may depend on whether chemical gradients existed in the sediment that could support metabolism. It may depend on whether textures are consistent with known abiotic reactions or require something more. These are not decorative details, they are the battleground. A biosignature claim is won or lost in details. That is why this story should not avoid technical reality, but translate it into suspense. The audience does not need to memorize every mineral. They need to understand that minerals are the witnesses. Some witnesses lie by accident. Some speak clearly only when placed beside others. A mineral alone may be ambiguous. A mineral in context may be decisive. The investigation is not about collecting impressive names. It is about reconstructing events. What happened to this rock? When did water touch it? What chemistry moved through it? Could microbes have lived there? If they did, what would they have changed? Could non-living chemistry change the same things? These questions turn stone into narrative without inventing anything. They allow the viewer to feel the weight of uncertainty as a sequence of tests, not as a vague mystery. The rock becomes a locked file. The rover has recovered it. The lab has not opened it yet. Every scene pushes toward that opening. The opening, when it comes, may be anticlimactic in appearance. No glowing object, no sudden scream from an instrument. Real laboratories move through protocols. Samples are documented, tools are cleaned, contamination is tracked, tiny fragments are allocated, measurements are repeated. Scientists argue over calibration, blanks, controls, and interpretation. Weeks become months, months become years. A major result may emerge not from one dramatic moment, but from a slow convergence of data that makes the old explanations collapse. Discovery by erosion of doubt. That phrase fits Mars. The planet has eroded its own evidence for billions of years. Science must erode the uncertainty piece by piece. What remains, if anything remains, may be the answer. This process can feel emotionally unsatisfying because it lacks a clean cinematic climax. But the slow version is more credible. A confirmed ancient Martian biosignature would need a long public life. It would be challenged immediately. Other groups would ask for access, replicate measurements, propose abiotic models, question contamination, test analogs, and compare samples. The claim would be strengthened by surviving those attacks. It would become accepted only by enduring. A discovery that cannot endure skepticism is not ready to become history. The rock has to survive the trial. Mars itself has already survived the fantasy. It has been imagined, romanticized, misread, mapped, landed on, drilled, and studied. The planet that remains after all that is more interesting than the old one. It is not a stage for easy alien stories. It is a world with a complex past, a damaged archive, and enough evidence of ancient water to make the life question scientifically serious. That seriousness is the point. A story about Mars rocks and ancient life should not feel like a gimmick. It should feel like standing in front of a sealed evidence locker, knowing that inside is either a false lead or a piece of history. The uncertainty is not a flaw in the drama. It is the drama. The rover's work gives that drama a physical body. Without perseverance, the story would remain abstract. With the rover, the question has wheels, cameras, a drill, sample tubes, and a route through Jezero. The machine moves through an environment selected for its ancient water history, finds rocks that preserve different pieces of that history, and creates a collection that may someday be returned. It turns a planetary question into a chain of tangible acts: drive, study, drill, seal, wait. Those acts are simple enough to picture and serious enough to carry the story. The waiting may be the hardest act. It belongs not to the rover, but to us. The sample tubes sit under Martian conditions while decisions are made on Earth. The gap between collection and return is filled with engineering studies, funding debates, redesigns, risk assessments, and scientific urgency. This is not the heroic simplicity of a single mission launch. It is a long institutional struggle to complete a question that has already begun. The rock is patient because it has no choice. Humans are impatient because we know what it might mean. There is a strange intimacy in naming samples and rocks on Mars. Chayava Falls, Sapphire Canyon. Names borrowed from Earth landscapes are placed onto Martian stone. The names make the evidence easier to discuss, but they also create a bridge between worlds. A sample cut from Mars enters human language before it enters human laboratories. It becomes a character in the investigation, not because it is alive, but because it carries unresolved meaning. That meaning has to be protected from overstatement. A rock with potential biosignatures is not a rock with life. It is a rock that meets enough conditions to deserve deeper analysis. The distinction may feel narrow, but it is the difference between science and theater. Every responsible telling has to preserve it. At the same time, the words should not be drained of wonder. Potential biosignature is a cautious phrase, but what it points toward is enormous. It means the rock contains a feature or substance that might have a biological origin. It means biology is one of the possibilities on the table, even if not yet favored or confirmed. It means the search has reached evidence with enough structure to demand a more difficult test. That is not dull. That is the edge. The edge is where the viewer should remain. Close enough to feel the possibility, far enough not to fall into false certainty. The narration should never pretend the answer is known. It should make the unknown feel heavy. Mars is good at heaviness. The planet's surface looks like aftermath. It has mountains too large for Earth's scale, canyons that tear across hemispheres, basins from ancient impacts, dust storms that swallow light, and valleys carved by water that is no longer there. Jezero is smaller than the planet's grandest features, but scientifically it has a different kind of force. It is not impressive because of size alone. It is impressive because it may preserve the right kind of past, a crater with a lake with a delta with sediments. Sediments with possible biosignature-bearing rocks. Rocks with samples. Samples with unanswered questions. That chain is the spine of the story. Each link narrows the scale and raises the stakes. From planet to crater, crater to lake, lake to delta, delta to rock, rock to core, core to molecule, molecule to interpretation. The search for life becomes a movement from vastness into detail. It begins with a planet and ends under a microscope. That is a powerful cinematic structure, because it reverses expectation. Space stories usually expand outward. This one collapses inward. The largest question in astronomy may be hidden in one of the smallest things on the screen, a rock. The camera can begin above Mars, looking down at Jezero's outline. It can move toward the delta, down to rover tracks, down to the drill hole, down to the core, down to a polished slice, down to mineral grains, down to molecular traces. At each scale, the question becomes more difficult and more intimate. The audience is not being shown a landscape anymore. They are being shown a possible memory. Manner in stone is never perfect. That imperfection is essential. If the rock preserved a perfectly obvious microbial fossil, the case would still need scrutiny, but the visual impact would dominate. More likely, any evidence is partial. It may have been modified by later fluids. It may be chemically altered. It may depend on relationships between features. The audience has to understand that ancient life detection is not like finding a preserved insect in amber. It is more like reconstructing a fire from ash after the rain. The ash may be real, the rain may have moved it, the story may still be recoverable. Mars's dry present helps in some ways, and hurts in others. Without active rivers and vegetation, ancient rocks can remain exposed. Without Earth-like weathering, some features may persist. But the thin atmosphere allows radiation to reach the surface. Oxidizing chemistry can damage organics. Dust can obscure, temperature changes can stress rocks. Mars preserves and destroys at the same time. This dual nature makes every sample both precious and compromised. A core taken from inside a rock is an attempt to reduce the compromise. It is still not untouched by history, but it is less exposed than the surface. That is why drilling is not merely a collection method. It is a preservation strategy. The sample tubes are designed to keep the evidence clean after collection. Cleanliness matters, because the search may involve organic chemistry. Earth is covered in life. Human technology carries traces of Earth. If a sample returns with organic molecules, scientists must know whether those molecules are Martian, meteoritic, instrument-related, or contamination from Earth. The chain of custody becomes part of the science. Witness tubes, sterilization, materials control, and curation procedures are not bureaucratic details. They are safeguards against fooling ourselves. The question is too important to be contaminated by carelessness. This is another reason the story has a detective quality. Evidence can be ruined, context can be lost. A careless sample is a weak sample. A contaminated sample becomes a nightmare. The mission has to think not only about discovery, but about defending discovery from future doubt. A biosignature claim will be attacked. It should be. Scientists will ask whether the instrument introduced something. Whether Earth materials were present. Whether sample handling changed the chemistry. Whether the feature existed in the rock before drilling. Whether the same pattern appears in controls. The more extraordinary the claim, the more intense the scrutiny. That scrutiny begins before the sample is even collected. It begins in how the rover is built, cleaned, documented, and operated. It continues in how the sample is sealed. It continues in how it is returned. It continues in how it is opened. Every stage is part of the evidence. This is why the public version of discovery can be misleading. A future headline may focus on the result, but the result will stand on years of invisible discipline. The careful target selection, the engineering of sample tubes, the rover's documentation, the avoidance of contamination, the preservation of geological context, the laboratory protocols, the peer review, the replication, the arguments. The real discovery is not one moment. It is a structure built to make a moment believable. Mars demands that structure because it is both near and alien. We know enough about it to form hypotheses, but not enough to trust easy analogies. Earth teaches us how life interacts with rock, but Mars followed its own path. Its atmosphere, gravity, volcanic history, impact history, radiation environment, water chemistry, and climate evolution differ from Earth's. Earth analogs are useful, but they are not identical. The investigation must use Earth knowledge without forcing Mars to become Earth. That balance is difficult. If every Martian feature is interpreted through Earth life, false positives multiply. If Mars is treated as completely unknowable, the search becomes paralyzed. The working approach has to be comparative, but cautious. What would life do in such an environment on Earth? What non-living processes on Mars could do the same thing? What measurements distinguish them? Which answer fits the whole rock best? The whole rock matters. Not just the dramatic feature. A spot's inside a rock is interpreted differently, depending on the rock's mineral composition, sedimentary structure, fluid history, and surrounding layers. A chemical concentration matters differently, if it follows a fracture or sits within depositional fabric. An organic signal matters differently if it is associated with certain minerals, or spread broadly. A possible biosignature is never just itself. It is part of a geological body. That is why sample return is not simply about more sensitive instruments. It is about preserving the relationships between features. Laboratories can cut the sample carefully, map it, and analyze it without losing the spatial context that gives meaning to chemistry. They can determine whether features are linked or coincidental. They can see whether a signal follows a boundary, fills a pore, coats a grain, or sits inside a mineral phase. At the scale of life detection, location is evidence. The difference between a biological and non-biological story may be measured in micrometers. This is hard to dramatize, but it should be dramatized, not by exaggerating, but by showing how small the courtroom becomes. The trial of life on Mars may take place along the edge of a mineral grain. The witnesses may be carbon molecules. The testimony may be isotopic. The judge may be a community of scientists arguing over whether abiotic chemistry has been exhausted. The scene is quiet, the stakes are enormous. That contrast is the heart of the documentary voice. The ancient lake at Jezero should not be presented as a lush Martian paradise. That would be dishonest and visually lazy. A better image is harsher: a cold basin under a young sun, water entering through a channel, sediment spreading into a crater, perhaps ice nearby, perhaps intermittent flow, perhaps long quiet intervals, perhaps chemistry changing as water interacted with basaltic crust. A place that may have been habitable not because it looked like Earth, but because it contained water, minerals, energy, and time. A microbial world does not need beauty. It needs opportunity. Opportunity may have existed in the sediments, at the interface of water and rock, where chemical gradients develop. Microbes on Earth exploit such gradients. They live where electrons can move, where energy can be harvested, where minerals and fluids create disequilibrium. If ancient Mars had similar disequilibria, it may have offered niches. But a niche is not an organism. A chemical opportunity can remain unused. That uncertainty keeps the story honest. The rover looks for signs that the opportunity may have been used. A potential biosignature is one such sign, but it must be treated as a beginning. The strongest future case would likely involve multiple indications: a habitable environment, organic compounds, mineral patterns consistent with low-temperature water chemistry, textures linked to those patterns, isotopic evidence difficult to explain abiotically, and a broader geological context that supports ancient microbial processes. No single piece does the work alone. The audience should feel that accumulation. The narrative can return to the rock again and again, each time with a different question. At the surface, it is a stone in a crater. In ancient Mars, it is sediment in a lake. Under the drill, it is a core. In the sample tube, it is sealed evidence. In the laboratory, it is a set of measurements. In human history, it is either a false lead, a record of habitability, or a possible sign that life is not unique to Earth. The same object changes meaning as the investigation deepens. That is narrative momentum. The rock does not need to move. The interpretation moves. Mars is silent, but the scientific story is not static. It advances through sharper questions. At one time the question was whether Mars had water. The answer became strong. Then the question was whether Mars had habitable environments. Evidence grew. Now the question is whether any of those environments were inhabited, and whether signs remain. That question is still open, and perseverance has made it more concrete. Concrete questions are dangerous because they can be answered. A vague dream can survive forever. A drilled sample cannot. It will either support the case, weaken it, or complicate it. That is why the rock is more threatening to the imagination than old myths were. Myths can adapt, evidence can disappoint, but evidence can also deliver. The possibility of delivery gives the mission its gravity. Somewhere in the sample collection may be a piece of Mars that becomes more famous after it leaves Mars than it ever was on the surface. Its name may become part of scientific history, or it may become an important cautionary tale. Either way, the rock's future meaning depends on human willingness to complete the return. The sample return debate is therefore not a side topic, it is the unresolved bridge. Without return, the evidence remains partly locked. With return, the investigation moves into a new phase. The debate over coast and architecture is frustrating. But it is not separate from the science. It determines whether the most promising samples become laboratory objects, or remain distant artifacts. A tube on Mars is not the same as a sample in a lab. That difference may be the difference between a headline and a conclusion. The rover can continue exploring, and it should. It can find new rocks, climb new terrain, study new contexts. Its extended journey beyond the crater floor and delta adds richness to the geology. But the life question still bends back toward the samples. The rocks, already collected, represent a rare opportunity. They are cleanly documented pieces of another planet, chosen for scientific reasons, preserved for the possibility of return. Each one is a time capsule without an opening date. That uncertainty has a strange beauty. It means the story is not over. It means the most important chapter in human understanding of Mars may not happen on Mars at all, but in a clean laboratory on Earth, under lights, among instruments, with people speaking carefully because the word life cannot be used cheaply. The lab scene should be imagined without melodrama. A sample arrives. It is handled under strict conditions. Scientists do not cheer before data. They measure, they prepare sections, they examine minerals, they test organics, they compare blanks, they run instruments, they publish. Others challenge them. Models are proposed, some fail, some survive. The answer takes shape slowly. If biology becomes the best explanation, it will be because non-biology was given every chance and still fell short. That is the only victory that matters. A rushed victory would be worthless. A slow one would be irreversible. Of course, even a strong biosignature would raise more questions. What kind of life was it? Was it related to Earth life through material exchanged between planets, or did it originate independently? How widespread was it? Did it exist only in brief windows, or persist underground? Did it die out when surface conditions changed? Are there other places on Mars where the evidence is stronger? Could life still survive deep below the surface today, protected from radiation and cold? A discovery would not end Mars, it would make Mars more complicated. Even a non-discovery would do that. If Jezero's return samples show habitable conditions with no signs of life, scientists would ask why. Was the window too short? Was the chemistry wrong? Was the water too intermittent? Did organic chemistry fail to organize? Did preservation fail? Did life exist elsewhere but not there? A negative answer would not be silence. It would be a different kind of information. This is why the rock matters regardless of outcome. It is a test of ideas that have floated above Mars for decades. The search for ancient life has often been discussed at planetary scale. But life, if it existed, would have been local. It would have lived in specific environments, under specific conditions, at specific times. A planet can be broadly hostile and locally habitable. It can have pockets of possibility. Jezero may have been one pocket. Other ancient environments may have been others. The sample from one crater cannot tell the whole planet's story, but it can tell one part with unprecedented depth. One part may be enough to break the loneliness, or deepen it. That emotional duality should remain present until the end. The viewer should not be led toward a fake answer. The viewer should be led toward respect for the difficulty of the answer. The mystery is not weakened by scientific caution. It is strengthened because the audience feels what it would take to believe. Belief is easy, evidence is hard. Mars has too often been given belief. The mission now is to give it evidence. The red planet has been a screen for human longing, but Perseverance treats it as a field site. It does not ask Mars to fulfill a myth. It asks rocks to preserve records. It looks where water once moved. It collects what may survive. It accepts that the answer may be microscopic and ambiguous. It accepts that the strongest tools are far away. It accepts that the most important discovery may require a chain of missions. That patience is almost anti-human. And yet it is one of the most human things we do. We send machines to a dead crater because we cannot live with not knowing. The rover itself is temporary, its wheels wear. Its power and systems age. Dust settles on hardware. Instruments have lifetimes, but the samples it collects could outlast the machine. If returned, they could sit in curated collections for generations. Scientists not yet born could study them with tools not yet invented. A rock drilled by Perseverance could continue answering questions long after the rover becomes another silent object on Mars. There is a melancholy in that. The machine may die beside the evidence it helped gather. The evidence may travel farther than the machine ever could. This is how exploration often works. The visible hero is temporary. The sample becomes permanent. The rover captures the imagination, but the rock may carry the legacy. Still, the rover matters emotionally because it gives the search a body in the landscape. Without it, Mars is distant. With it, we can see the drill holes, the tracks, the rocks chosen and rejected. The patient movement through a crater older than human history, by an almost meaningless margin. Perseverance makes the abstract question physical. It shows the cost of asking carefully.
A careless question
could be asked from Earth. A careful one needed a rover. The question now rests in the samples. There is a scene that returns again and again in the mind. A core sample held in harsh light. Red dust around it, the rover somewhere behind, the crater silent. The sample is small. It has no drama in itself, yet the entire history of Mars may narrow into its layers. A lake, a delta, a river valley. A period when water existed. A period when chemistry may have been rich. A period when life may have had a chance. Then loss, drying, exposure, cold waiting. The sample is not just a piece of rock. It is compressed time. If ancient life ever touched it, that touch has been translated into geology. Biology would no longer be soft. It would be mineral. It would be preserved not as movement but as alteration, not as a cell but as a trace, not as a voice but as a pattern. This translation is why the investigation feels so severe. We are not looking for life, we are looking for what life becomes after a planet dies. That is the sentence Mars forces on us. The beauty of the search is that it does not need to exaggerate. The real version is already extraordinary. A rover in an ancient Martian lakebed has collected samples from rocks that may preserve evidence relevant to ancient habitability and possible biosignatures. Some features are intriguing enough to demand deeper study. The samples remain far away. The return is difficult. The answer is unknown. Nothing more needs to be invented. No fossils, no Martian creatures, no hidden civilization, no dramatic certainty. A rock is enough. The restraint gives the story its credibility. The tension comes not from claiming too much, but from knowing how much is at stake if the evidence eventually holds. The audience can feel both the nearness and distance of the answer. The rock has been drilled, the tube has been sealed, the sample may already exist. But the conclusion remains out of reach. That is a perfect scientific cliff edge. The story can end there without pretending to end the question. Mars is still silent. Jezero is still dry. The rover continues or rests under a thin sky. The sample tubes remain as small sealed arguments against human impatience. The ancient lake is gone, but its sediments remain. The possible biosignature is not confirmed, but not dismissed. The sample return question remains unresolved, and with it the fate of some of the most important rocks ever collected. The audience should be left with the feeling that the answer is not in a speech, it is in a stone. If the stone comes home, it may disappoint us. It may humble us. It may teach us that Mars came close to life and stayed empty. It may teach us that geology can mimic biology with unnerving skill. It may remain ambiguous, or it may carry a signal that survives every test and forces humanity to say, carefully, after years of doubt, that Earth was not the only world where life once wrote itself into rock. Until then, the strongest sentence is also the hardest one. We do not know, but the question has a location now. It has a crater. It has a delta. It has a rover track. It has a drill hole. It has a sealed sample. It has a name. It has a future. If humanity can complete the chain, Mars will not answer because we want it to. It will answer only if the evidence is there. And somewhere in the cold silence of Jezero Crater, inside a small core of stone, the evidence may already be waiting.